I'm Bridget Green.
And I'm Kevin Weber, and on today's episode of The Bring Up, we're bringing up supercomputing at Supercomputing 2024.
Say supercomputing one more time.
Supercomputing. It's a lot of leaves, Bridget.
I heard you want to talk about technology. You don't have to twist my arm too hard on that topic.
Should I leave?
Are you looking for secrets?
Bring up. Bridget. She's dead.
You may not like it, but this is what peak performance looks like.
Hi everyone, and welcome to The Bring Up.
We are at the SC24 Supercomputing Conference, which, as you probably guessed, is all about science of supercomputing.
And for the last 25 years, there's been one surefire way to know that your supercomputer is indeed the most superlatively super of them all. And I'm talking, of course, about
The List. Top 500 is a top 500 list of the fastest supercomputers in the world, and AMD is currently driving the number one fastest supercomputer, El Capitan, or El Cap, if you're buddies like we are.
Oh, and don't forget, we also power the number 2 fastest supercomputer, Frontier, and the number 5, one of my favorites, number 8,
Yep.
and number 10.
Okay, we're going to have to stop listing there because we're just going to be listing supercomputers all day.
And I could.
El Capitan is comprised of over 10 million AMD EPYC and Instinct cores for a total of up to 2.7 exaflops of raw computing power.
And don't worry, we're going to talk through exactly what that means a little bit later in the show, because if you're like me, you've heard of supercomputing, but personally, I didn't really know how a system like El Cap actually works or why you would even need that much compute power.
Yeah, you can always say it's a really, really big, super fast computer, but that doesn't really answer the question of what kinds of problems a system like this is architected to solve.
Yes, and we're taking a cue from our supercomputing counterparts and distributing the workload for this episode. So I'll be interviewing engineering fellow Nick Malaya, who's a high-performance computing specialist.
And I'll be interviewing our friend of the show, Apostolos Kotsiolis, to help put things in perspective.
Take it away, Kevin.
We're here at the booth here at SC24, and I'm asking you a very important question. Can you explain to me what flops are?
Flops, okay. Flop stands for floating point operations per second. And as you know, computers are really good at doing math. That's the main thing that we designed them to do. Floating point numbers can be high precision or low precision, depending on how many decimal points they have. And they're extremely important for scientific and engineering calculations. So flops is essentially how fast can you do those floating math operations. The scientific workloads, which could be high performance computing, engineering simulations, molecular dynamics, weather, all this kind of stuff. Those are floating point math.
What are workloads that are calculated in a supercomputer where the time criticality is really important, or the weight of what the simulation actually means? What do those workloads look like?
So supercomputers are big computers, and they are designed to solve very big problems. Problems that your laptop and my desktop will take years and years to solve, right? So, for example, one thing that is very common on running on a supercomputer is weather prediction. So if there is a hurricane, you're trying to simulate the different paths that the hurricane can take. Time is of the essence.
Weather prediction calculations are hugely computationally expensive. Let's say that a highly accurate hurricane simulation takes 10 to the 20 flops. I ran a couple benchmarks on some of the high-performance systems that I have access to and got the performance numbers on them. So my home desktop processor clocked in at about 805 gigaflops. My workstation at the office clocked in at about 3.3 teraflops, and our EPYC server clocked in at 17.8 teraflops. Now, these are all very performant systems, so let's see how they match up against this enormous problem. Running on my desktop at home, it would take nearly 4 years to complete this calculation. On my Threadripper system, it would take almost 350 days. On the EPYC server, it would take 65 days, and on the El Cap supercomputer, it would take only 57 seconds. Obviously, taking 4 years to complete a critical weather event calculation just is not tenable when lives are at stake. So you have the fastest supercomputer in the world. Now what? Let's throw to Bridget interviewing Nick Malaya.
Nick, thank you so much for taking some time out of your busy supercomputing to chat with us.
Absolutely.
How do you define supercomputing as a supercomputing professional?
Yeah. I think there's a few things that go into it, but at a high level, I think a key essence is the parallelism of a big computer. So, any of the individual parts may be something you could even get as a commodity part, but they're typically networked together in a very large and parallel way. And that influences everything about the design. It influences the algorithms, the kind of software you have to write for it, all the way down to, of course, the networking technologies and how the pieces interact with each other.
I've been doing a lot of research on this topic.
Excellent.
And have learned that a supercomputer is not just a bunch of computers stacked on top of each other.
Yeah.
So what sort of things are you keeping in mind when you're designing and implementing workloads onto a supercomputer?
So ultimately, when we work with a Livermore National Lab, like with El Capitan or Oak Ridge, and our partners like Hewlett-Packard Enterprise, we sit down and say, what are their goals for this system? And then we kind of talk about what is possible and how can we architect around it. And then there's just a huge amount of design considerations that go into it, which is part of what's really interesting. It's so multifaceted. So on one hand, you of course, AMD, we have compute technologies. We're telling our partners, here's what we think is possible from a compute standpoint. They might have a physics goal or some sort of simulation campaign they want to run. And then we work with the integrators to say, look, what kind of cabinets can we build? What's the cooling solutions? Where is the system going to be located? Because there's actually power considerations. How much power can we draw off the grid for this particular system? So those all kind of come together in this very high dimensional optimization problem we do. And then ultimately we kind of all work together to stand it up. And what you conceive of when you start, many years ago, I started working on these large exascale systems in 2018. The end result isn't quite the same. So you have to go with the flow as well and kind of be agile as you stand it up, as you learn, and then really deliver something that's great, but maybe not quite what you envisioned originally.
I think it's interesting, you mentioning that when you were starting out, petaflops was kind of the new hotness, and now we are in the exaflop era. What is it going to take, and what sort of challenges will we have to overcome to get to that next echelon of supercomputing?
Two ones that I think are really important, performance per watt. We have to continue to drive down the energy that's used by these systems. Right now, systems like Frontier or El Capitan require tens of megawatts of power. The human brain, which is on the order of tens of watts, so it's just much more efficient. I think we've got a proof that there are more efficient computational resources out there. But that's something that we're really looking at. It's an area that AMD really continues to focus on in terms of that. But then there's also aggregate performance. We have to find ways to just deliver more performance on these parts. And I think AI is a really interesting guide there. AI has been using a lot of these reduced precision data types. They were going to smaller bit widths, and they find that there's much higher performance that you can get out of that. It causes a big speed up. It happens to also, because there's reduced data motion, there's less to compute, it's very performance efficient, so the performance per watt also goes up. So I think areas like that are very interesting to explore, but many simulations can't use those reduced precision data types. They use FP64, double precision, and that's what HPL, the metric of the top 500, is based on. So we'll have to see as a community, can these simulations, these science simulations, use that, or will they continue to use FP64? And I think it's going to be a mix of both. So there's a lot of learning and research we'll have to do to get to the next prefix.
Well, we'll have to have you on again in 10 years to tell us if it worked or not.
I hope so. I think it'll be less time than that. Hopefully.
Okay. You let me know.
Absolutely.
We'll bring you back.
Thank
you so much, Nick.
Thanks,
Bridget.
Kevin. It's really nice being right in the center of so many people who are making the tech that is going to change the world.
Yes, we hope you're leaving this episode a little more confident in what supercomputing is and a lot more excited about what it can do.
If you don't ever want to miss a future episode, follow us on YouTube, LinkedIn, and Instagram, and use 2.7 exaflops of computing power to find that bell icon.
And as always, we have a little treat for those of you who stuck around to the end of the episode, and we'll see you next time.
The tour of LCAPs is pretty cool, but I don't actually see a way out of here.
Well, it was a discounted tour price, so you get what you pay for, Kevin.